Our primary focus for today is electron configurations. Now, electron configurations take those ideas that we talked about yesterday, the ideas of quantum numbers, the ideas of capacity for an energy level, capacity for a sublevel, and allow us to describe the electrons in an atom in more of a bulk form. So if I have an electron, or if I have an atom with 35 electrons in it, this is how those 35 electrons are arranged in terms of their energy levels and their sublevels. That's what an electron configuration does. It gives us a distribution of those electrons based upon the different orbitals, or again, more specifically, we would probably take this word out and talk more about the different sublevels of an atom as opposed to their orbitals. And so that's what an electron configuration does. Now, we're going to use this as a stepping stone, because ultimately when we talk about electron configurations, what this will allow us to do is will allow us to split our arrangement of atoms and their electrons into two groups. There'll be the groups of electrons that have nothing to do with bonding. We call them core electrons. And then there'll be the electrons that do all of the bonding, and we call those outer or valence electrons. And it's those valence electrons that we'll be talking about next week when we talk about bonding and molecular arrangements and those kinds of things. So let's look at electron configurations. Now, in electron configurations, we understand that there are two things going on. First of all, there's something called the Aufbau Principle. Now, the Aufbau Principle is a rather simple concept, and it's an intuitive one. You probably could have come up with this one on your own. Aufbau just happened to come up with it first and put some solid ideas to it. That's why it's named after him instead of you. But the idea is this: we fill up orbitals from lowest energy to highest energy. So every sublevel that we use, every sublevel that gets filled, we start with the lowest energy sublevels and we build up to the highest energy sublevels. And usually that means that we start at the lowest energy level and work our way up to the higher energy levels. The second principle is that in Hund's rule, I'm going to change this wording again. Electrons are going to fill degenerate sublevels evenly. Now, what do we mean by degenerate sublevels? Well, let's say that we have a p sublevel. And so in my p orbitals, I've got my p sublevel, I've got 3 orbitals, 1, 2, 3. And I want to fill these with electrons. Well, electrons are negatively charged, right?
Mm-hmm.
What happens if I put 2 negatively charged things in the same space?
They repel.
They repel. And so what Hund's rule says is to avoid repulsion, instead of pairing up electrons like this in filling one orbital in the sublevel, then the next, then the next. What Hund's rule says is no, we don't do this. What we do instead is we're going to fill these evenly. So I'm going to put an electron here. I'm going to put an electron here when it's necessary. I'm going to put a third electron there when it's necessary. By doing so, I keep these negatively charged particles as far apart from each other as possible. And that's really the key to Hund's rule. We got electrons, they're negatively charged, like charges repel. Let's keep them as far apart as possible. Now, if the need comes where we have to start doubling them up, we will. But we're going to wait until that is absolutely necessary. Hang on one second. All right. So that's the Hund's rule there. Any questions about these two principles?
No.
No.
Now, one thing I will point out, drawing electrons in this kind of way, this is something called orbital notation. And orbital notation is when we show each energy level, each sublevel, and how the electrons are arranged in those sublevels. The convention for showing electrons is that all electrons are shown as being spin up first. So the reason I drew all up arrows initially here was to abide by that convention. And if you were ever asked, I don't think there are any questions in our homework about this, but if you were ever asked about quantum numbers using orbital notation, this is how you would want to do it. If the last electron is an up arrow, then that means that m sub s is positive 1/2. That's spin up. If the last electron is pointing downward, then it's spin down, and would be negative 1/2. The other thing that often would get associated is from orbital notation, we can be given values of m sub L, and the convention there is just numbering them numerically from smallest to biggest, left to right. So this first spot would be -1, this second spot would be 0, this last spot would be +1. And so let's just say, for the sake of argument, that this is a 3p sublevel, and this is the last electron in that 3p sublevel. Then the 4 quantum numbers that we'd be talking about here would be n equals 3, since it's the third energy level, L equals 1, because it's 3p, m sub L is equal to -1, because this last arrow is in the -1 spot, and then m sub s is equal to -1/2, because it's a downward facing arrow. So, like I said, I don't think I put any questions like that in the homework set or in the electron configuration quantum number set. But if you did see something like that in the homework or in, the extra practice problems in smart work, that's how to handle those. That's how to tackle them. Any questions about that?
No.
All right, well then let's move on. And talk about how do we apply the Aufbau principle. Well, the Aufbau principle tells us that there is a specific order of filling as far as energy levels and sublevels are concerned. And one of the ways to do it is to use this slash system. And so this slash system is very common. Every textbook has it. I don't tend to focus a whole lot of time on it because, frankly, there's an easier way to do it. But what you can do is if you draw out each energy level, 1 through 7, and all of the orbitals that are possible in each of those energy levels, then by drawing a series of diagonal slashes, you would come up with the correct rank order of the orbitals as they fill based upon their individual energies. Now, what you'll notice about this is that there are some spots in here that are not quite what we would call making a whole lot of sense. For example, you'll see that we fill the 4s energy level, or sublevel rather, before the 3D gets filled. And again, based on the Aufbau principle, the reason for that, the 4s sublevel is lower in energy than the 3D. The 3D requires a little bit more energy to put electrons in it than the 4s does. And we can see that this anomaly is consistent. If I take it to the 5s, 5s is lower in energy than 4D. 6s is lower in energy than 5D or 4f. We actually see that the F sublevels are quite high in energy. In fact, we don't actually see the 4f until after the 6s has already been filled. And we don't see the 5f used until after the 7s is filled. And so the Aufbau principle just gives us that information. It says, okay, this is what is reality. This is how they fill up in order. Now, the reason I don't use this, because A, it's just rote memorization. It doesn't really do anything. And B, there's an easier way. And we'll get to that easier way in just a second here. Hund's rule, we kind of talked about that already. You can see that as we build up according to our Aufbau principle, we fill the 1s first. We start to fill the 2s. The 2s fills up. Once we fill up the 2s, we start to fill up the 2p orbital by orbital in that sublevel until we have to pair them up. Once we pair them up, then we move on to a new energy level, the 3s, because that's the next lowest in energy. And so when we're discussing every single electron in an atom or an ion, we call that a complete electron configuration. That is, we're going to represent every single electron in that species, whether it's an atom or an ion. But like I said, there's an easier way to do this. The easier way to do this is using the periodic table of elements. Because if you look closely at the periodic table, what you should notice is that there are some groupings here that have numbers associated with them that match up with the numbering that we saw in the quantum numbers when it came to maximum number of electrons. If I count up the boxes here, there are 2 boxes in this zone. There are 6 boxes in this zone. There are 10 boxes in this zone. And if we count up Now, if we count up all the lanthanides and actinides, we'd have 15. We have to recognize that one of these, either lanthanum or lutetium, belongs in this spot right here next to hafnium. One of these, either actinium or lawrencium, belongs in this spot here. And so when we do that, we see that there are 14 that are actually part of this grouping here. Now, which one actually belongs in this spot? Your guess is as good as mine. There's a lot of debate about whether lanthanum is actually in this block of 10 or in this block of 14, and it's lutetium here instead. Good news for us, we don't do very much rare earth chemistry. And so that debate is largely left for the theoretical PhDs of the world, as opposed to the majority of us who live on planet Earth. But you can see by using this, we can look and see, okay, 2 electrons. Well, 2 electrons matches the S capacity. 6 electrons, that matches the P capacity. 10 electrons, that matches the D capacity. 14 electrons, that matches the F capacity. And so what we can do, I'm going to actually clear this, is we're going to do 2 things. If you have a periodic table handy, I would strongly suggest getting one out and making some kind of marking on it. Because this is a visualization and the picture is so much easier to interpret if you actually have the visual representation in front of you. And so we're going to go ahead and draw this out again, and I'm going to recolor each zone so that they're all different from each other in some kind of way that we can point to and recognize. Now, the other thing I want you to do while we're doing this, you can see that helium I have moved over here for the purpose of electron configurations. And the reason for that is helium doesn't belong in this block. It doesn't have 5 other partners in its energy level. It belongs over here next to hydrogen in this particular case. But what I want you to do also, label down the side. If your periodic table doesn't have numbers on it yet to represent the periods, it needs to. Now these numbers, these period rows, represent the world's crappiest N. These represent energy level. So these are values of N. Now the red zone here represents the S sublevel. And the S sublevel always abides by the energy level that it is in. So when I'm describing hydrogen and helium, I will be describing electrons in the 1s sublevel. When I'm describing lithium and beryllium, I will be describing electrons in the 2s sublevel. Over here in dark green, we have the p sublevel. And again, it matches up with the energy level as well. So the boron through neon, those are represented by 2p orbitals, the 2p sublevel. Thallium through radon here, these are represented by the 6p sublevel, and their electrons are found in orbitals in that 6p sublevel. In the middle here in hot pink are transition metals. These represent the D sublevel, and their representation in terms of energy level is always 1 off, n minus 1. So what I mean by that, scandium. Scandium is found here in the 4th row, the 4th period. But the electrons that are represented in scandium are not 4d electrons, they're 3d electrons. I take 4, take 1 off of it, and that describes the sublevel. So this sublevel here, we can think of, this is the 3d sublevel, this is the 4d sublevel, this is the 5d sublevel, this is the 6d sublevel. Lastly, baby blue here, the F sublevel, and these are n minus 2. So we can see that the lanthanide series should be in period 6. N minus 2, 6 minus 2, these actually represent 4F electrons. Actinide series actually represents 5F electrons. So 4F, 5F, those are the ones that we're working with there. Now, how do we use the periodic table to build configurations? Well, it's simple. We always start at the top. We always start with the lowest energy, and we build and build and build and build until we get to where we're going. So just as an example here, let's look at germanium here real quick. If I wanted to do the electron configuration for germanium, I would start at the hydrogen, represent those electrons. I would keep going through all of the electrons on the periodic table until I got to germanium. What would that look like? Well, starting at the top, I have 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, and then finally we get to where germanium is in the 4p. Now that's not the only thing that we have to do. We also have to represent the number of electrons in each energy sublevel. But again, luckily for us, that can be done by counting. And so if I look at 1s, well, that's 2. 2s has 2 in it. 2p has 6 in it. 3s has 2 in it. 3p has 6 in it. 4s has 2 in it. 3d has 10 in it. And then when I get to 4p, germanium is the second in this big block. So the last configuration is 4p2. So whenever I get to the block that contains the element that I'm studying, I just count the number of positions to get to where it is. And that tells me how many electrons are in that block. Every other block that precedes it, generally speaking, is full. And so I can use those max capacities to my advantage there. I already know what the maximum number is. I could count it. I could count, okay, there are 1, 2 here in the S. There are 1, 2, 3, 4, 5, 6 here in the P. But that's the way I would do it. And so the superscripts That is how I tell how many electrons are in a given sublevel. And that's what I have to do ultimately. Any questions about that?
No.
Now, the other thing that we can do, always is a good way to double check ourselves, make sure that we're in the right direction, is we know that an atom of germanium is going to have 32 electrons in it because it has 32 protons. If it wasn't that way, then we would be dealing with an ion and not an atom. But since we're looking for 32, I should be able to count all of my superscripts, add them all together, and they should get to 32. Tells me I'm at least heading in the right direction. So 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 18 plus 2 is 20, 20 plus 10 is 30, 30 plus 2 is 32. That matches up the 32 I had there. And so that's always a good way to double check yourself when you're doing an electron configuration, is to kind of just, okay, do my electrons add together to the right end? Let's do a couple more examples. What is the complete configuration for zinc? So if we go back to the table here, we're looking for zinc. Zinc is right there. If we follow the pattern, 1s, 2s, 2p, 3s, 3p, 4s, 3d, that's how it's going to end up looking to us. And now we just need to fill it in all the way. 1s, well, that's 1s2 because it's full. The next one's 2s, 2s2 because it's also full. Then 2p, it's full, so it's 2p6. Then 3s, 3s, and it's 3s2. Then 3p, and it's full, so 3p6. Then 4s, and it's full, so 4s2. Okay, and now we come to zinc's sublevel, 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So zinc happens to have a full 3D subshell as well, because it is the last element in that block, in that group. And so that's the complete configuration for zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, next one. What is the complete configuration for argon? Again, we're going to do the same kind of thing. Argon's here, it's number 18. So we're just going to kind of follow along. I went 1s, 2, 2s, 2, 2p6, 3s2. And now I got to argon, 3p, 1, 2, 3, 4, 5, 6, 3p6 is that configuration for argon. right? And the last one is asking for the orbital notation for scandium. So if you're asked to draw orbital notation, again, it's the same kind of idea, just instead of doing the superscripts, you're going to draw lines to represent the orbitals. So I've got 1s, I've got 2s. Each s sublevel has only one orbital in it, so I'm only going to put one line. I've got 2p. P sublevel has 3 orbitals in it, so I'm going to put 3 lines. Then 3s. Then 3p. Then 4s. And then finally 3d, which is where we can stop because that's where scandium is. And the d sublevel has 5 orbitals in it. So I need to draw 5 of these little lines. Now, one approach that we can do is when we know what the configuration is, we can always work backwards from it. So in the case of scandium here, I know that the last configuration is going to be 3D1. And so where that comes in handy here is I can put in my 3D1 like that. And I know that that's the only sublevel that's going to be partially filled. And every other sublevel that came before it is going to be completely filled. And so I can just fill in the rest this way, working my way back until I get all of those lines filled in with those arrows. Now, if I wasn't being asked to do an orbital notation, if I was just going to do a complete electron configuration like we had done in the past, same kind of idea applies. We can look at it here and see we've got 2 electrons in the 1s. We've got 2 electrons in the 2s. We got 6 electrons in the 2p. We've got 2 electrons in the 3s. We've got 6 electrons in the 3p. We've got 2 electrons in the 4s. And then we've got just 1 lone electron in the 3d. And so this and this mean the same thing, tell the same story. The only difference is that the orbital notation gives you just slightly better, slightly more information, in particular about the last electron here, in terms of if I was going to try to quantify that electron's environment using quantum numbers, I could do so. All right, any questions about those 3 examples?
Just on the last one. So the 3, so that would be a positive 1/2 then, since it went up.
Right. By convention, every first electron in an orbital is spin up positive 1/2.
Okay.
It is generally considered that the spin up electron is slightly lower in energy than the spin down electron.
Okay.
Other questions?
No.
All right, let's keep going then. Now, you can imagine, most of the examples that we did, we picked on examples that didn't have a whole lot of electrons. I mean, the biggest that we got was, germanium had 32, zinc had 30. And you can see that those electron configurations were starting to get long. Now, imagine if you had to do lead or radon or any of those, other ones, it'd become a long exercise and a pretty redundant one at that. And so luckily there is a shortcut. The shortcut is something called a noble gas configuration. What a noble gas configuration does is it basically sets and assumes that all of the inner electrons, all of those electrons that kind of make up those configurations before, can be summed up by a noble gas configuration. So if I take, for example, this calcium, and I look at its full configuration, calcium is 1s2, 2s2, 2p6, 3s2, 3p6. If I compare that here, what I would find is that this part of the configuration that's boxed in is the same as the electron configuration of argon. And so instead of writing all of this out, I'm just going to write in brackets argon to represent these first 18 electrons. And then I'm going to write about the stuff that's interesting, the stuff on the outside, the stuff that could change, that actually interacts. And so this sets up for us the distinction that I've been alluding to between core electrons, that is electrons in the inner energy levels of an atom, the ones that are held tightly by the nucleus and therefore do not interact very much with anything and are, as far as bonding is concerned, relatively useless. And comparing that against valence electrons, these guys, which are on the outer part of the atom and therefore are much less tightly bound to the nucleus and a lot more easily interactable with other electrons. These are the ones that ultimately do the bonding. Now, to do a noble gas configuration, all you need to do, going back to the table itself here, let's say that you're doing the configuration for zinc. You go backwards until you hit a noble gas, and that noble gas becomes the beginning of your electron configuration. So zinc went from 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 to argon, 4s2, 3d10. So condensing it down, making it simpler, is in our distinct advantage, and noble gas configurations will be used often to describe electrons, especially in heavier elements, because of the very nature of having to write out that really long configuration. So let's do a couple more problems together. Determine the noble gas configuration for vanadium. So again, I would point you to a periodic table of some kind here. If I'm looking at vanadium, vanadium is element number 23. I go backwards from element number 23 and I end up at argon, element number 18. And so my noble gas configuration starts with argon in brackets. And then if I go from there, it would be 4s2 and 3d1, 2, 3, 3d3. Now the other one on that page was arsenic. Noble gas configuration for arsenic, which let's do this in a different color. Again, we go backwards from arsenic. We end up also at argon. Argon 4s2, 3d10, 4p1, 2, 3. So, like I said, this is a real shortcut. This can really be helpful in terms of shortening up these electron configurations while still giving us the exact same information. Because on the whole, we really don't care about these first 18 electrons. We care that they are there, but in terms of their reactivity, they don't do anything. All right, any questions about noble gas configurations? All right, let's stop there. Let's take a 10-minute break, come back at 10 after 10, and we'll discuss anomalies, and we'll also get into ion configurations. So how do our electron configurations change when we start looking at ions instead of atoms? So 10:10, we'll come back and look at this a little bit more closely. Go ahead and take a break. All right, let's get restarted here. All right, so unfortunately, electron configurations, and actually no thing in any science class can ever be quite as easy as it seems. There are a few anomalies that are in existence with regard to electron configurations. And the ones that we're going to focus on are the ones that are a little bit more common. We talked about that idea of closeness, the closeness between the between the s orbitals in in an energy level and the d orbitals in that energy level near it. And this is where the bulk of the anomalies that we're focusing on are actually going to take place. Because those energy levels are actually quite close to each other in energy, there are occasions where the 4s, which is usually lower in energy, and the 3d, which is usually higher in energy, actually will either even up or actually flip in terms of their energetics. And so what happens in those circumstances is we see electron migrations. An electron, since it's now beneficial to go into the d orbital, is going to go into into a d orbital instead of an s orbital. And so depending upon how many migrate, we call these either S1 exceptions. S1 exceptions occur when we have one electron that migrates, and S0 exceptions occur when we have both s electrons migrating. Now, there's only one S0 exception, and that is palladium. All the other ones on this list are S1 exceptions. And I'll show you this list, but like most things with the periodic table, like most things in general, a picture usually helps a lot more than just a rote list. I'll show you what I mean. Here again is our periodic table of elements. Now we've already pointed out in our periodic table that palladium is our lone S0 exception. Our S1 exceptions, which I'm going to highlight here in a different color, do have some pattern to them. Not saying it's the easiest pattern to follow, but there is a pattern to them. So chromium, niobium, and molybdenum, they are right here. We also see that there's a block around copper, silver, gold, and platinum. Which will fill in there. And ruthenium and rhodium are the other two that exhibit this behavior. Now, to me, I'm going to give you a picture, and I'm hoping I'm not dating myself too much here. Any of you like to play video games?
Sometimes.
I'm a child of the 80s and the 90s. My favorite video game of all time is Super Mario Brothers 3. And this has always looked to me, if you're familiar at all with any of the games in the Super Mario franchise, especially the older games on the original Nintendo system, there were always these tile blocks all over the place. You had to jump on them. You had to jump over them. You had to jump around them. You had to run on them. And this is always what this has looked like to me. This has looked like there's a very particular level in Mario 3 that has a series of patterned shapes that look exactly like this. And the S1 exceptions have always reminded me of those. It's a funny picture. I'll see if I can find a picture that shows you what I'm talking about. If you have no idea what I'm talking about, this is kind of a boring conversation to you. But this is always what has been reminded. But if the visualization doesn't work for you, there's another way we can look at it. If we think about it from a configuration standpoint, we can actually rationalize more than half of these exceptions. If I look at this group right here, This would be the D sublevel and the fourth electron in that sublevel. So chromium and molybdenum, these would be what we would call D4 elements. And if I look at orbital notation for the D sublevel, putting in 4 electrons would mean that we have a sublevel that's pretty close to being filled at least halfway. And if we throw in further that our s electrons over here, we can see that if a migration occurs, if this guy goes over here and we go to this configuration here, can you see how even that is? Can you see how this actually would minimize repulsion? Because now all 6 of these electrons are all separate from each other. That's the benefit. And so in the D4 block, what we see more especially is that the s orbital and the p orbital, or the d orbital rather, are pretty much energetically neutral toward each other. They're about the same. And so it's almost like they act as they are all degenerate with each other. They all spread out. And we see a similar kind of phenomenon in the copper group here. These are D9 configurations. And with the D9 configuration, what we see is that initially speaking, we would have a configuration that looked like this. But with that migration, this s electron goes over here, and in doing so, we've now completely filled the d orbitals and left the s orbital underfilled, but still it has something in it. And so from that perspective, the D9 orbitals, we can rationalize those as well. So D4 and D9, that's half of them right there. We can rationalize based on their orbital notation why those migrations occur. And even for palladium, we can rationalize it as well in the same kind of way, because if I look at the anticipated configuration for palladium, it would look like this, S2D8. But if we get a double migration, if we turn this into S0, and this is the only one that does this, if both of these electrons migrate, and completely fill the D sublevel, then what I get on the other hand is a completely filled D sublevel, which is stable, a completely empty S sublevel, which is stable, and therefore a pretty happy configuration. Now, you might be asking yourself, well, why doesn't this extend more into period 6 and period 7? Well, in period 7, the thing we run into down here is these guys are all radioactive. And so the actual chemistries, their electron configurations, they're degrading so fast that we really don't have I wouldn't say we had a real strong handle on whether or not these exceptions exist. The other thing that we have to consider in these two is that once we get into period 6, we start finding the F block being used more often. And there's a reason we're not talking about the F block. And the reason we're not talking about the F block is that the number of anomalies that exist in the F block makes this look like child's play. There are quite a few more that we would have to worry ourselves with. And again, the chances of you doing anything with terbium in your lifetime, I've never even seen terbium. The chances of doing anything with some of these elements is pretty low. They're very rare. There's a reason why the lanthanides and actinides are sometimes referred to as the rare earth metals. Their usage and their abundance, and therefore your chances of actually working with them, are relatively low. All right, any questions about these anomalies? All right, I'll take silence as no. Here's what I want you to do. Take a few minutes and write out the complete and noble gas configurations for these 4 atoms: copper, indium, bromine, and gold. I'll turn off my mic, let you talk to each other. And actually, for the sake of our time here, let's just focus on the noble gas configurations. You'll get plenty of chance to do lots of practice with complete in the post lecture that's due tonight. Let's do the noble gas configurations only. So I'm going to mute myself and let you talk your way through this. And I'll step in if you guys get stuck. Go ahead and go.
So for copper, if you go backwards to the noble gas, it would be argon. So it would be in brackets, AR in brackets, and then it would be 4s2 and then 3d10. If you guys agree.
Yes, you just wrote it the short way.
Yeah, because he said with the noble gas.
Okay.
Yeah. Somebody else want to go for the second one?
Malaz, what did you say was the 4S configuration?
4s2.
Anyone want to jump in on that one?
For indium, no, that not for indium, right?
No, I was referring to copper.
Oh no.
Oh wait. Ugh, duh. Never mind. S.
Oh, that's only 30.
Yeah.
Oh, that's why. So that's okay. So 29. It'll be 18. It'll be was it 9? D9. So everything else the same, but it'll be D9. No. 11. No.
10, yeah.
It'll be 11. D11.
Wait, what? It can't be 11. There's
Oh,
only.
because she said 4s2. Okay, no.
It's 4s1 because I forgot of the exception.
Okay.
So copper is one of those exceptions. So yeah, I forgot about it. So it'd be 4s1 3d10.
All right, go ahead and move on to indium.
That would be Kr in brackets, and then 4s2, 5s2, 4d10, and 5p1.
Oh, yeah, that's what I got.
And then for bromine, it would be brackets AR, and then 4s2, 3d10, 4p5, I believe. Yep.
Did you say 5s for the idiom? Did you say 5s2 and 4d10?
Mm-hmm.
I thought it'd be 4d. No, that's only 48. It's supposed to be 49. So is it?
Chasney,
We skipped the whole front of the
Chasney, how many elements are in the D block?
Couldn't it be up to?
How many boxes are, if I'm looking at the D block, how many
12.
boxes are there?
It'd be up to 12 because 3 through 12. Or D orbital, which is 10.
Yeah, it's 10.
Okay.
It doesn't.
But 13 through 18 is the P. And
Yeah.
Indian is in P.
Yes, 13 through 18 is P, and indium is the first in the P block.
Right, with 49 electrons. But what I got was 48. I mean, what I got was 48 when I calculated the krypton with S2 and D10. Because krypton has 36. S2, that's 38. And then plus 10 is 48. It needs to have 49, right?
Right, so that's where the 5p1 comes in.
Okay, yeah, okay.
That gives you the 49th.
Yeah, did she say 5p1? I just didn't hear it.
She did.
Oh, sorry. Okay, I just didn't write it down. Sorry.
You were saying 48, and I think everyone else was thinking you were saying 4D8. Like
No.
that was the configuration.
No. I didn't hear her say 5p1. I just missed it.
And then for gold, I would say it's 6s1, 5d, 9. Oh, forgot the xe. 5d9. Wouldn't it be 5d9?
So, why is it S1 not S2?
Because it's one of those exceptions.
Okay.
Yeah.
you're missing something here.
Or gold?
Uh-huh. Count up your electrons.
Oh, the
What's
F.
it? What's in between barium and hafnium? Yeah.
I think it's 4. No, yeah, 4F14.
Okay.
Yeah.
Okay, now, if Chasney doesn't catch it, I'll catch it myself here. You're still short. If you do the math here, that's 78 electrons. Gold has 79. You're right. It's an S1 exception. Where did that other S electron go? It's a migration, right? S electrons migrate. Where do they migrate to?
The D orbital.
The D. So it had 9 before, because it's in that 9th column. It's under the copper and the silver. Adding one more, that gets it to 10. And now, if you do the math, 54 electrons for xenon, plus 1 is 55, plus 14 is 69, plus 10 is 79, which is how many we should have for gold.
Oh, okay. And so then for the S0, that one will not travel because that one will not migrate anywhere because it's 0.
So if it's S0, that means that both of the electrons migrated. They both went to the D.
Oh, okay.
Okay. No, the ones that have no migration are the ones that are S2.
Oh, okay, I see.
So like indium and bromine, they didn't have a migration. Now, part of the reason they didn't have a migration was because the d orbitals were already filled, but they still didn't have a migration nonetheless.
Okay.
It's when S is 1 or S is 0, that's when we see that migration to the D. And those occur in those select transition metals that we pointed out earlier.
Okay. So then would PD be 3D10 also?
Lead or palladium, yes.
Okay.
Palladium would be krypton 4d10.
Okay.
There'd be no S electrons. So you could either write that as krypton 5s0 4d10 or just krypton 4d10.
Okay.
All right. Any questions about these?
No.
All right, let's move on. So the last bit that we're going to talk about here are ions. Now, ion configurations are not too terribly difficult if you know and can follow a couple of relatively simple rules. The first rule is that the charge is going to help us to dictate the direction that we move. So when we have cations, that's positively charged ions, we're going to subtract the number of electrons equal to the charge. Now, in most cases, that is, most things that are not transition metals, this means that we're going to have a filled outer shell. And so what we usually will see in both of these cases is noble gas configurations are going to be the primary thing that we see. So I take away electrons, and that usually ends up getting me to a noble gas configuration. I add electrons in the case of anions, and I usually get a filled outer shell that gives me to a noble gas configuration as well. Simple, elegant, and so long as we're not talking about transition metals, we can use this periodic table as the means to do it. We just move that many boxes over, and we write the electron configuration for that element. So for calcium, for example, calcium 2+ is its ion. Well, if I scoot to the left 2 places, because calcium 2+ ion has 18 electrons, the configuration for calcium 2+ ion is the same as the configuration for argon. And so I can either write it as that noble gas configuration, argon in brackets, or if I had to write the complete configuration, I would write the configuration for argon, which is 1s2, 2s2, 2p6, 3s2, 3p6. Same thing with anions. Anions we're going to see, primarily in that nonmetal block. And we're just going to add those electrons on. And so that usually will end up with us in a noble gas configuration as well. So take fluorine, for example. Fluorine with 9 electrons, fluoride ion with 10 electrons, the same noble gas configuration as neon. And so I could either write neon as the shorthand configuration, or I could write its longhand configuration, 1s2, 2s2, 2p6. So when it comes to ionic configurations, it's usually pretty easy. Let's do a couple of quick examples. So for the calcium ion, calcium 2+, I go backwards 2 spots. So I'm here at calcium. I go back 1, 2 places. I end up at argon. And so the noble gas configuration for the calcium ion is just simply argon. For the sodium ion, sodium 1+, go back again. Sodium is 11 electrons. 1+ would mean 1 fewer, so 10 electrons. We're talking about the configuration of neon. For the chloride ion, Cl-, we had 17 electrons. Adding 1 would give us 18 electrons. 18 electrons, that's the noble gas configuration of argon. And for phosphide, 15 electrons in phosphorus, add 3 more, that gives us 18. And here we are at argon again. And so for these kinds of configurations, when we're talking about the main group, that is the elements that reside in that S block, that's groups 1 and 2, groups 13 through 18, we tend to land on noble gases. And so the configurations for those are really easy to draw out. And that's what I mean by this little notation here. Noble gas configurations dominate ion configurations. That's what that means. It's the thing that happens. When we get to transition metals, though, it's a little bit different. Transition metals are always going to form cations, so we're always going to be taking electrons out of transition metals, just like we would take them out of any other metal ion. The other thing that's going to happen, though, is that distance from the nucleus is going to matter more than energy. So even though those transition metals have electrons in the d orbitals that are technically higher in energy, we need to keep in mind that as far as that energetics is concerned, the d orbitals and the s orbitals are pretty close to each other in their energy. But the advantage of taking away the s electrons, even though they are technically lower in energy, they're further from the nucleus. And since they're further from the nucleus, they're going to be easier to pull out. They're going to be easier to excite and take out of the electron, or excuse me, take out of the atom. And so for that reason, what we will see is that when we are dealing with transition metal ions, we will always see that the outermost energy level loses its electrons first. So take, for example, chromium. Chromium-3 ion. What's going to happen first is that it needs to lose 3 electrons. It's going to lose this 4s electron first because it is the furthest away from the nucleus, and then it'll lose 2 more out of the d orbital here. And so we see this in a lot of transition metals, where we're going to lose those s electrons first, then we're going to come back and we're going to take the d electrons if necessary. And so it's for this reason why, if you look at the electron configurations, and if you look at the common ions for most transition metals have a positive 2 electronic state. And the reason why, well, there are 2 electrons in the s orbital that get taken first. So the majority of them take on a positive 2 state because, well, that's the electron that gets taken. Why does silver only take on a positive 1 state? Well, silver is one of those rare S1 exceptions. And so it only has 1 s electron to lose. Its d orbital is completely filled. So it loses that s electron, and then it's happy, it's content. It's got a filled a filled 4th energy level. And so it's stable. We don't see silver forming positive 2 or positive 3 or positive 5 electronic states. It only does the positive 1. And so that's the reason why. And so you got to be careful about those, in particular dealing with these transition metal ions, because your instinct is to take away these first because they're the higher in energy, but you have to take away the ones that are higher in energy level, not just higher in energy. Let's take a look at some more examples. And again, in the interest of brevity here, because we're running out of time, just do the noble gas configurations. So talk your way through these again. You'll notice that we've got a mixture here of transition metals and main group elements. So take your time, make sure that you've got it right, and go ahead and talk it out here.
Are we starting?
Yeah, go ahead.
Yeah.
So for BE, it would be
Would it just be helium?
Yeah, helium. That's what I got. Because it's just 2. You got a minus. Yeah. HEN brackets. Yeah. That's what I got.
This one I'm not quite sure. So we're supposed to take it out of the S first?
Yeah.
AR. Because if you go 3 back, or no, not AR. Wait, either CL or AR. I don't know.
I thought you were going to do the AR, but you'll take it out of like S to take it out of the S.
Yeah, but if you take it out of the S, you go calcium and what do you call it? Potassium.
Mm-hmm.
And then so those 2 are out, and then you still have one more to get rid of. So then you go into the P, but I don't know what it would be.
But with the CR, when we did the CR3 plus, we still had AR, like we still use that, and then you just take it out of the ones that you add.
Wait, what?
Okay, when we did the CR3 plus ion in the transition metal example, they still put AR in there, like they still had AR. They just took it out of the. I can't explain it right, but you're saying that we start off with what? CL or S? I said AR, but
This one was put in there because this one's tricky and kind of deceptive.
Okay.
Okay. So I put on the board here. That is the configuration for the gallium ion. Argon 4s2 3d10 4p1.
yeah.
That's the the full atom configuration. Now, I did not say, I did say for transition metals that we take away the S first. Is gallium a transition metal?
No.
No. Now, it's not going to follow exactly the same rules. We're not going to end up at a noble gas here because we've got more than 3 electrons here after the noble gas. But which 3 electrons do we take away? We take away the highest energy and the highest energy level. So highest energy, which of these 13 electrons is highest in energy?
The 4p.
Yeah, the 4p. So that one's gone. That's the first one we would lose. It's the one that is highest in energy level. Now I need to look at the remnants here. Between 4s and 3d, which one is higher in energy level?
3D. 4s.
Okay, 4th energy level is larger than the 3rd energy level.
Oh, okay.
So the 4th energy level is what we're going to use. So 4s, those 2 electrons go away as well. There's my 3 electrons that I lost. So the configuration for the ion would be argon 3d10. So the gallium has lost its valence electrons. It's lost its electrons in the 4th energy level. It has not lost any of the ones in the D block.
Okay.
And it's going to gain some stability from that because remember, the 3D completes that 3rd energy level. So it's pretty stable in this state, which is why gallium only forms the positive 3 ion. It doesn't form any other ions.
So if we were doing this backwards, like if it gave you AR 3D10. Oh, never mind. Okay. I was going to say, how would you know that it wouldn't be zinc? But
well, because
the 4s would be there to tell you.
So you're right. this would be the same electron configuration as a zinc ion. But that's okay. It is possible to have multiple species that have the same number of electrons. Completely fine. We call that a phenomenon known as isoelectronics.
Okay. So for the next one, I believe it is NE.
That's what I got.
And the next one, XE.
Yeah.
I think TI is 81, right? I can't tell if that's TL or TI. Oh, never mind. TI is over here. Is this one of the trick ones?
I got AR in brackets 1s2.
Wouldn't you go back 2 spaces though?
What you mean? 22 minus 2, 20 CA.
Wait, what did you say the original one you said was?
AR in brackets 1s2.
Where did you
Oh
get
my God, it's wrong? What? What is that?
So that is the noble gas configuration for titanium atom. Now this is a 2+ ion.
Yeah.
Which 2 electrons get lost?
Oh, you just wrote it the original way, not the. Oh.
Which 2 electrons get lost? Do we lose the D electrons, the S electrons, or one of each?
You lose the one of each. No, you lose.
the D one?
I don't. I'm confused now because
I mean the S one.
Okay.
Yeah,
So this
that
is the
should be my
same.
guess.
This is the same argument that we had in the gallium.
Oh.
Do I take from the 3rd energy level, or the 3rd energy level, or the 4th energy level?
Well, it
gonna
makes
take
sense to where it's located, so it does make sense.
I'm going to take from the 4th energy level because it's higher in energy. The electrons are further from the nucleus. Okay. All right. So for gold, we had xenon, 6s1, 4f, 14, 5d, 10. That was the configuration for gold atoms. What would it be for gold plus 1 ion? Where do I lose an electron?
So again, does it just take it from the highest
It does.
energy level?
So if I'm taking from the highest energy level, which energy level do I take from?
That would be the F. I do believe. Oh no, 5. Oh no, the 6s. Okay, so it's the 6s.
Yeah.
Okay.
Always look for that biggest principal quantum number. Always look for that biggest energy level.
But if it's the same energy level, like the gallium, you would take based off of the L number?
Yes. Yeah.
Okay.
So in gallium, we took from P first because P is higher energy than S.
Okay.
Okay.
So
Okay.
the N value trumps the subshell letter then, right?
Yes.
Okay.
Yeah. We only go to subshell. We only go to subshell designation in the event of a tie.
Okay. All right.
Like, can't you look at it? Okay, because can't you look at it where, okay, AU is located in the F, so that way that's what you end up with. But you wrote it in, like, I'm used to like writing it in order, like D comes before F, but you write it F comes before D.
Well, I'm writing it in order according to the Aufbau principle.
Oh, okay.
So I had it this way because 6s is lower in energy than 4f, and 4f is lower in energy than 5d.
Okay.
However, when it comes to ionization doesn't care. It cares about energy level. And so energy level is the first thing we look at. And the one that has the biggest energy level is the one that gets lost first.
Okay. I think I'm just looking at it a certain way.
Now,
Okay.
if you put it in the other way, if you went
Like SPDF, like
SPDF, you could do that. It would be technically considered out of order. So I don't know how SmartWork would respond to that. But I mean, I guess you could. The problem there is you don't want to get it confused in terms of what is the order of filling.
Mm-hmm.
All right, we've got one more here.
Okay.
Brett, did you have a question?
I was just going to ask a silly one. I think this is what I got confused on on the last one. So I'm looking at the periodic table, and it looks like the F group or whatever looks like it was cut out of energy levels 6 and 7, but I have wrote down that they're actually 4 and 5. Why is that?
Because the F sublevels are so high in energy that in terms we start seeing F orbitals in the 4th energy level. We start seeing F orbitals in the 4th energy level. But they're so high in energy relative to the other ones that their order doesn't come up until after the 6s has been filled.
Okay, so they're just kind of a weird thing on their end then.
Yeah, so I mean, if you think about the energetics around D and F are a little bit screwy compared to S and P. S and P are very, very well behaved.
Okay.
S, then P, S, then P, S, then P. Well, D and F follow in line there, but they're not nearly as close in energy as S and P are. And so that's when we get that little bit of staggering in the D subsection and that lot of bit of staggering in the F subsection.
Okay.
All right. For copper, again, let's start with the primary configuration of the atom. So argon, 4s, 1, 3d, 10. This is the configuration of the atom itself. Now I need to lose 2 electrons. So where do those electrons come from?
A 4s. Well, one of them does.
Okay, so I lose one of these in the 4s. That only gives me 1 though.
And
so
then
I'm going to need to take 1 out of the 3d as well. And so the configuration here would be argon 3d 9. All right, this was a lot to swallow today. I don't know what was better, doing it all in one large session, or my original plan was to break it over, do half of it yesterday, half of it today. I don't know which one actually worked out better.
No, this is.
But you kind of got the full poison pill here. Now what you got to do is you got to work on it. And so what I'm going to turn over to you to do on your own There is some information in here. We talked a little bit about this already, about how you can get quantum numbers from the orbitals. There are a few slides here about periodic trends and how you can use the periodic table to determine trends in energy and so on. I'm going to tell you that you can skip trend number 4. We're not going to talk about electron affinity. As far as a periodic trend goes, it really isn't much of one. So what I'd like you to do over the weekend, go through and read up on these periodic trends: effective nuclear charge, atomic size, ionic size, ionization energy. If you have questions, we'll do a little bit of an overview and review. We'll do some practice problems first thing Monday. But then I want to get straight into chapter 4, talking about bonding and molecular modeling and that kind of stuff afterward. Any questions?
Just one. Can you show me again the slide that has the exceptions? I've got my periodic table. I just want to mark that down real quick.
Okay. I have to erase it in between, but I can rewrite it here quickly.
Okay.
All right. So palladium was your S0 exception. And then you had your D4 block, starting with chromium, molybdenum, and niobium. Your D9 block, starting with copper, silver, gold, and platinum, the precious metals. And then kind of bridging it in between, you had ruthenium and rhodium. And these are your S1 exceptions.